has yttrium, terbium, actinium, rubidium, boron, gadolinium, niobium, iridium, strontium, and silicon, and silver, and samarium, and bismuth, bromine, lithium, beryllium, and barium.
I'll start this video talking about a concept that I mentioned a couple of videos back, and that concept was what happens if we excite an electron. So what happens when we excite an electron? What happens with the energy that is released once it becomes unexcited again? So what I mean by that is this was the shells. We've got our sodium atom here. Sodium atom has 11 protons, which also means it has 11 electrons. So you can see it has 2 in the first shell, 8 in the second, and 3 in the first shell, 1 in the third shell. So what happens if we add energy by using, for example, heat, like flame? What happens if we add energy to this electron? Well, it will become excited. What that means, it will go from this shell to a different shell because it's absorbed energy, it's become excited. And after that happens, what will happen next? So now it's in its, we call this its excited state. And we call the original state, we call that the ground state. So the ground state is the original state. So in this case, it's shell number 3 for this electron. And the excited state was the state where it's at when it's after it's absorbed that heat energy. Once it's released that heat energy, what can happen is that can jump back. Let's say it jumps back down one shell, because it won't stay excited for long. It'll stay excited for a very short period of time, and then it will jump back down again to release some. And once it does jump back down, it will release some energy. Now the energy obviously can come in heat, but in this case it will come in a different form, not in heat energy, but in light energy. What that means is we can actually see it emitting light. So let's say, for example, this electron, once it jumps back after it's gotten excited, jumps back towards its ground state, it will emit, let's say, orange light. Now the reason I'm mentioning this is, and this says the same thing here again, we've got electrons, and they can jump different levels. So for example, this electron might jump 1, this electron might jump 2, and this electron might jump 3 levels. And when they come back down, they will emit different colors of light. And this sodium atom, for example, could emit these different wavelengths of light. So remember, light itself, if we put, for example, if we put normal white light in a prism, this here is a prism. If we put normal white light into the prism, what will happen is it will show the different colors of light, because light itself is made up of different colors. Altogether it's white, but it has the colors of the rainbow. So in this case, what this means is this thing here, this is the normal spectrum, the whole spectrum, all different possible colors. But as you can see, each element has specific type of wavelengths. So for example, sodium emits green light. So these small frequencies of green light, these small frequencies of yellow light, and this frequency of orange light. For example, this frequency of orange light we might call 616, because this is 600, this is 620 right here, and just before in the 616. And then you can see hydrogen would have different types of emissions. So when they become excited and when they drop back down, they have different types of light that they emit. And calcium has different types of light that it emits when it becomes first excited and then it drops back into its ground state. Same with magnesium and neon. This is basically what that means. Every single atom has its unique range of light that it emits when it comes in contact with heat and reaches the excited state and drops back into its ground state. So we can use that knowledge to figure out, for example, what's in a sample. Let's say we take sample 1. Right? So sample 1 has only sodium. So we put sample 1 into this kind of device, which we call atomic emission spectroscopy. Right? So atomic emission spectroscopy. What we do is we have a heat source, which is this source here. We have our sample. So in sample 1, it's all sodium particles. And then we vaporize it, which means we make it into gas. So you can see here all these gas particles. In this case, sample 1 case would be sodium. We let it emit light. So now it's going to emit light. It's going to emit these different frequencies of light. And that will then hit a prism. Right? The light will hit a prism. And we can see what kind of light comes out. So we can see if the light that comes out here on this side are the colors that would correspond to sodium. So if only these colors are emitted, not all the colors, but only these colors, that means in this sample, only sodium was present. So that's how we can figure out what kind of elements or atoms are inside an actual sample. Let's say we take sample 2, which has some sodium, some calcium, some magnesium, and some neon in it, right? Which basically are all the ones we have here. So we do the same thing. We put it under a flame to vaporize it, right, to make it excited. So here it's in its excited state. That means once it's excited, it will eventually drop back. So it will release energy by dropping back into its ground state or close to its ground state. And once it does that, it emits light, right? So in this case, we have all different types. So we're expecting it to emit all these different types of wavelengths of light. And we can see that when it comes to the prism, right? So it'll hit the prism, and then we can see what comes out on the other side. And if it's all these different types of wavelengths, that means we've got these different types of elements present. So what we can use this technique for, which is called atomic emission spectroscopy, is we can see what kind of elements are present, and that's a form of qualitative analysis. What that means is we can figure out what is inside the sample, so what is inside, and we can also use it to see how much of it is inside. For example, we can see if this is a very sort of not too bright line or a very bright line. It's possible to also figure out how much of it is inside. If it's really bright, that means it's more inside. If it's really sort of not bright, that means it's less inside. But overall, we can use something else to figure out how much of it is inside, right? But we use atomic emission spectroscopy to figure out what is inside, using that kind of technique I mentioned just beforehand. But we don't really need to know that much about atomic emission spectroscopy, but there was a reason why I mentioned all this, because it's important to know kind of the first step to see how we can do the second step, because the dot point itself says describe the use of atomic absorption spectroscopy in detecting concentrations of metal ions in solution and assess its impact on scientific understanding of the effects of trace elements. And so we have to actually talk about not atomic emission spectroscopy, but atomic absorption spectroscopy. And that's what I'll talk about next. So we're going to talk about atomic absorption spectroscopy now. And that's going to be basically relying on the first part of how we managed to figure out what kind of wavelengths that these different types of atoms emit. Right? That was the emission spectrum. So in the first part, we figured out the emission spectrum. We figured out that an excited atom will release energy, and by doing so, will release these different wavelengths of light. And that we can figure that out, and we can figure out basically the identification code for that atom. So if we have these different wavelengths present, that means this atom is present. Now we can use a principle which basically says that a spectrum emitted by an excited atom, the excited atom, will be absorbed by a ground state atom. So if we have this spectrum and we send it through a bunch of ground state atoms, so normal atoms, they will actually absorb some of this light. Right, so the absorption spectrum refers to not the excited. The excited atoms are the emission spectrum. The ground state atom talks about the absorption spectrum. So the ground state atoms, which are the ones which are not excited, they will absorb light from the excited atoms. So this emission spectrum of the excited atoms. I'll go over in a second again a bit more what that means. But we can use that knowledge to basically have a device which allows us to look at a very small sample, concentration, and figure out how much of it is inside. And we do so by using this technique here, which we call atomic absorption spectroscopy. So there's a couple of different parts to this. First, we need to have a light source. Now, we often use a hollow cathode lamp. And how this works is basically it's a light source that emits light, a light spectrum of a specific atom. So for example, let's say we have a hollow cathode lamp that emits calcium. The spectrum, it won't emit calcium atoms. It will emit the wavelengths that calcium atoms will absorb, the ones which are in the ground state, right? So we will go for these ones here. Emission spectrum. So the actual lamp will just produce these different types of wavelengths, because we're only wanting to find out if there's actually calcium in that, how much calcium there is in that sample. So this is the first step. We've got the lamp, and the second step is we have this furnace, which basically is a heat source, and this is where we put our sample in. Now the actual dot point says we need to talk about metal ions and how we can use a device or a technique to figure out how many of these metal ions were in the actual solution. Now, first thing we have to do, and that's why we have a flame here, is actually turn the calcium ion into the calcium atom, because all of this is what I talked about beforehand, the ground state and the excited state. That doesn't talk about ions, sorry, it talks about atoms. So first thing we have to do is we have to convert ions into atoms, right? And that's what happens at the flame. So the flame in this case, what the flame does, it actually converts the sample from ions into atoms. It does not make it excited. So all of these atoms are all in their ground state here. They're not in the actual excited state. Remember how absorption works with the ground state atoms. It doesn't work with the excited state atoms. So we don't actually want to have them in the ground state. That was for the atomic emission spectroscopy, not for the atomic absorption spectroscopy. Right, so in this case, we're going to make sure we can convert the calcium ions into calcium atoms. That's done with this flame here, which is often roughly 1000 degrees Celsius. And that brings us lots of atoms which are in vapor forms. That means they are gaseous. So the sample initially was a aqueous solution, which means it was liquidy, and then we turn it into gas. Now the next step would be to have this light, which is of its specific wavelengths, right? So these ones which are absorbed by calcium atoms. So we have this light here. This is the light which is the same as this light here. It's passing through the flame, and the flame itself has all these vapors, these atom vapors, right? And these atom vapors are calcium atoms, which are in its ground state, right? Remember, the ground state ones will be the ones which will absorb different types of spectrum. These ones here, they will absorb the emission spectrum. So we have this light here, which comes from the yellow cathode lamp, and what comes out will be a bit less light than what came in. And the reason why is because there's going to be, so there might have been 10 of these light rays go in and maybe only 5 come out. And the reason why is because these atoms will have absorbed some, so they will have actually consumed some of them. Right? So some of them will have been absorbed that light, which is the reason why we have less going in than coming out. Less going out than coming in, sorry, other way around. And that was the second step. That happened here at this part here. The next step is, I'll kind of put the prism and the lens all in one. What happens first is the light, the remaining light. So this is the remaining light. And the remaining light will pass through the lens and then through a prism. And the reason why it passes through a prism is because the prism is the thing that will, this light here has these different types of wavelengths. So if this, for example, with a calcium one, you might have, these are not actually the calcium emission spectrum, I'll just as an example. But let's say this were the ones for calcium. So it might have red, green, yellow, and blue, and dark blue. So all in one. So all of this will be all the different types of wavelengths. Once we put it through the prism, it will make it into different sections, convert into different sections. And what we can do now is we can just absorb one section. So right now, we're just going to absorb that yellow section of the emission spectrum, right? So we've changed it, and you can see here, this is where it goes after it goes through the prism, where it's split into the different wavelengths. It goes to photomultiplier, and the photomultiplier is aiming just to collect this one here, the yellow one. The other ones won't actually be absorbed. And now we'll get a reading. So let's say now, for this sample, it's told us there is 0.1. So this is the reading we get, 0.1. This happens at a photomultiplier. And now we've basically completed the whole thing. And I'll explain how we can use all that to figure out how much is in a different sample. Because that value doesn't tell us too much. But once we actually test it for concentrations we know. So let's say we have different concentrations we're testing. So here we're testing concentrations that we know of, calcium being 1.1 part per million. ppm means part per million. So what we're doing is we're testing 4 samples, right? For these 4 samples, we know the concentration. So we know the concentration of calcium in each of these samples. Let's say we have 1 part per million in the first one, 2 parts per million in the second one, 3 parts per million in the third one, and 4 parts per million in the last one. We're going to do this whole step for each one of them, one after the other. So first we're going to do this one, and we'll do the whole thing, and we'll get let's say we get a reading of 0.1 for the first one. So it has absorbed 0.1 of all of this light, this initial light. Now the second one, the 2 parts per million, let's say it absorbed, second one it absorbed 0.2 0.19. And for the third one, the 3 parts per million, it absorbs 0.29. And let's say we do the same thing the fourth sample. I put in that whole in the incinerator, do the whole procedure, and it might be a 0.38 value. So what we can do now is we can just do these. We can use these standard samples where we know the concentration of. These are standard samples where we know the concentration of. But now we can figure out the absorptions of these different samples. And then if we have a sample, so now after we have this whole data, we can use a sample, an unknown sample. Right, so an unknown sample, put it into this device and see what absorbance we get. Let's say we get this unknown sample which we don't know the actual values for, the concentrations for. Let's say we get an absorbance value of 0.12, right? So then we can use this actual data to figure out, okay, well, this was the standard one. These ones are the ones we knew exactly how much concentration it had. And if it has 0.12, that means it will be more than 1 part per million, less than 2 parts per million. It's closer to 1 part per million because 0.1 is closer to then 0.19. So it'll probably be about 1.2 parts per million, right? So after we've done the standard samples, we can then figure out unknown samples. And that's why this device is very useful, because it helps us to figure out not qualitative, but quantitative. And quantitative, remember, quantitative means measurement. So not as in what is inside, but how much of it is inside. The first technique, the emission spectrum spectroscopy, atomic emission spectroscopy, we found out what is inside, what actual atoms are inside. But with the atomic absorption spectroscopy, we can find out how much of it is inside using this procedure I just mentioned. Right? I'll quickly sum up the first part of this dot point, and the second part we'll cover in the next video. So describe the use of atomic absorption spectroscopy in detecting concentrations of metal ions in solution. So in this case, what we talked about first was atomic emission spectroscopy, and that was used to find out what is actually inside a sample. And we did that by figuring out what kind of different types of wavelengths that the excited electrons would emit. So for example, sodium would emit these different types of wavelengths. So if we had one sample and we had all these different types of wavelengths that were emitted, we could figure out what was inside that sample. That was the first thing we did. And then the information that we gained from the atomic emission spectroscopy, we could then use to find out not just what is inside, but how much of it is inside. But we did that with a different technique called atomic absorption spectroscopy. Now, for the atomic absorption spectroscopy, what we did is we had the information of the emission spectrum of different types of atoms. So for example, let's say this was the emission spectrum for the excited calcium atom. And we also knew that the ground state calcium atom, so the calcium atom which was not excited, would absorb the same type of spectrum. Right? So in this case, you can see this is a spectrum if we have light sent through it, and light that doesn't come back, light that was absorbed by the actual calcium atoms, was the same light that was emitted by the excited calcium atoms. So knowing this information, we could set up a different type of procedure, which consisted of a halo cathode lamp, which had the different types of wavelengths of the atoms that we're looking for. So for example, if we wanted to see how much calcium was in the sample, we would use the emission spectrum light of calcium. So in this light, what would come out would only have the emission spectrum of calcium in it. We'd send the light through this device here, which is an incinerator, which would basically have the aqueous sample of a solution, and this hot flame would turn the calcium ions into calcium atoms. They would still be ground state, they won't be excited, they will be ground state. And that's important because that means that the actual light that will pass through will be partially absorbed by these ground state atoms, which means that the light that doesn't pass through, the light that gets absorbed, can tell us how much of that calcium is inside. And we figured that out by using this prism here, which we call a monochromator. It's basically the whole device. This is a simplified version, simplified diagram. And then we analyze only one specific wavelength of the whole emission spectrum. And in this case, for example, let's say if it has 0.1, we figure out if it has a concentration of 1 part per million, that would give us an absorption of 0.1, whereas if it had more, it would be different absorption. So that's how we could use that information to kind of gain understanding of not just what is inside, but how much is inside. And for this, you need to know, for this part, you need to basically know the different parts that come with this technique, and the kind of the theory behind how this works as well. I hope that was useful.
Thank you for watching.